Welcome to your personalized deep dive. Today we're tackling electrochemistry. You've sent us some fascinating excerpts, and I'm already buzzing with questions. It's like chemistry, but with electricity. What's not to love?
Exactly. It's where those chemical reactions and electrical energy kind of intertwine. We'll explore how reactions can create electricity like in batteries and how we can actually use that electricity to drive reactions that wouldn't normally happen.
So, okay, let's start with the basics then. What is electrochemistry exactly?
Well, it's the study of how electricity and those chemical reactions are interconnected, a sort of two-way street where one can be converted into the other. And it's got huge real-world significance. We're talking the production of metals, chemicals, those all-important batteries, plus its role in environmental technologies and even biological processes inside our own bodies.
Wow, that's a huge scope.
Yeah.
So where do we even begin with something so vast?
Well, at the heart of it all are electrochemical cells. These are the devices where that conversion between electrical and chemical energy actually happens.
So like a battery.
Exactly. Batteries are a great example of one type of electrochemical cell called a galvanic cell. These use spontaneous chemical reactions to release energy and create electricity. But there's another type called an electrolytic cell, which uses external electrical energy to drive reactions that wouldn't normally occur on their own.
Like a battery in reverse.
Yeah.
Can we stick with those galvanic cells for a bit?
Mm-hmm.
I'm really curious to understand how they actually generate that electricity.
Absolutely. Let's look at a classic example, the Daniel cell. It's a simple setup with two compartments or half cells. One has a zinc electrode dipped in a zinc sulfate solution, and the other a copper electrode in a copper sulfate solution.
So basically like two beakers with metal rods in them.
Essentially, yes. And what happens is a spontaneous chemical reaction. The zinc electrode tends to lose electrons, which is called oxidation, and those electrons travel through an external wire to the copper electrode.
So the zinc electrode is giving up electrons. Where do they go?
They flow through that wire to the copper electrode, and there they're picked up by the copper ions in the solution. This is called reduction, and it actually causes copper metal to deposit onto that copper electrode.
So you get a flow of electrons from the zinc to the copper, creating an electrical current. That's pretty amazing. But wait, wouldn't that cause an imbalance of charge in those solutions?
You're right, it would. And that's where the salt bridge comes in. It's a tube filled with the salt solution that connects those two half cells, allowing ions to flow back and forth and maintain that all-important electrical neutrality.
So the salt bridge keeps everything balanced kind of behind the scenes. This is all happening spontaneously, right? It's like built-in energy production. But there was something else you mentioned about the Daniel cell, something about applying an opposing voltage.
Right. Even if you apply an external voltage that opposes the cell's own natural voltage, the reaction doesn't just stop, like, immediately. It keeps going until that external voltage reaches a specific point.
So it's like the reaction has a certain stubbornness to it. What about those electrolytic cells, the ones that work in reverse? Do they have any interesting quirks like that?
Well, imagine reversing the situation in our Daniel cell. If you apply a high enough external voltage, you can force the reaction to go in the opposite direction. You could make zinc deposit onto the zinc electrode and the copper dissolve back into the solution.
That's like rewinding the reaction. But why would we want to do that? Seems like we're working against the natural flow of things.
That's precisely how we create some important materials. Electrolysis, the process of using electrolytic cells, is how we produce pure metals like sodium, magnesium, and aluminum, as well as chemicals like sodium hydroxide, chlorine, and fluorine. It's a fundamental industrial process.
So we're harnessing electricity to create these valuable materials. But I have to admit, thinking about all this electron flow and opposing voltages is making my head spin a bit. Is there a way to understand the driving force behind these reactions, maybe, a little more clearly?
Absolutely. That brings us to the concept of electrode potential. Each electrode, when dipped into its solution, develops a potential difference with that solution. Think of it like a tug-of-war between two tendencies. The metal ions in the solution want to deposit onto the electrode, making it more positive, while the metal atoms in the electrode want to give up electrons and become ions in the solution, making the electrode more negative.
So it's like a battle for charge at the surface of the electrode. And what determines who wins?
That's the electrode potential. And when we talk about standard electrode potential, we're looking at a specific situation where all the concentrations are at a standard value. We use a reference point called the standard hydrogen electrode, or SHE, which has a potential of 0 volts.
So we measure everything against SHE, like a ruler for electrode potential. What does she actually look like?
It's a platinum electrode, coated with platinum black, dipped in an acidic solution with hydrogen gas bubbling through it. It's all very carefully controlled.
Sounds high-tech. So we compare other half cells to SEEA to determine their standard electrode potentials. What do those values actually tell us?
They indicate how likely a species is to gain or lose electrons. For instance, a high positive standard electrode potential means the species really wants to gain electrons, making it a strong oxidizing agent, like fluorine. On the other hand, a low standard electrode potential indicates a strong tendency to lose electrons, making it a powerful reducing agent, like lithium.
So it's a ranking of electron affinity. That's incredibly useful. But we've been talking about standard conditions. What happens when the concentrations aren't at those standard values? Does that change things?
Absolutely, and that's where the Nernst equation comes in. It allows us to calculate the electrode potential at non-standard concentrations.
Okay, I'm sensing some math coming. Can we stick to the concept without getting bogged down in the numbers?
Of course. The Nernst equation basically tells us that electrode potential is affected by concentration. For example, in our Daniell cell, if we increase the concentration of copper ions, the potential of the copper electrode will increase. And if we decrease the concentration of zinc ions, the zinc electrode potential will decrease.
So the concentrations can shift, that tug of war you were talking about. That's fascinating. But I'm also wondering about how these electrochemical reactions relate to the idea of chemical equilibrium. Is there any connection there?
That's a really insightful question. In fact, the Nernst equation also helps us understand what happens when a galvanic cell reaches equilibrium. Remember how we mentioned the voltage dropping to zero in the Daniell cell? That's the point where there's no net reaction happening. And the Nernst equation can actually be used to link that standard cell potential to the equilibrium constant of the reaction.
So we can calculate the equilibrium constant from the cell potential. That's incredible. It's like connecting different areas of chemistry in a new way. But now I'm also thinking about the energy involved in these reactions. Can we actually quantify the energy changes associated with these electrochemical cells?
Absolutely. That brings us to Gibbs energy, often denoted as delta G. This is a thermodynamic quantity that represents the maximum useful work that can be obtained from a cell.
So it's like a measure of the cell's potential energy, the energy that's available to kind of do work.
Exactly. And there's a direct relationship between that Gibbs energy change and the cell potential.
I'm seeing another equation on the horizon. Again, concept over calculation, please.
The equation basically shows us that a more negative Gibbs energy change corresponds to a more positive cell potential. And like with the equilibrium constant, we can actually calculate the Gibbs energy change from the cell potential.
So we can use these electrochemical measurements to kind of understand the energy dynamics of reactions. That's pretty powerful. We've been so focused on the electron flow and the reactions themselves, but what about the solutions where those reactions are taking place? Do their properties affect things?
You're absolutely right. We can't forget about the solution itself. And its ability to conduct electricity, its electrolytic conductance, is a crucial factor.
So some solutions are better conductors than others. What factors affect that?
Well, there's several things. The type and concentration of ions are major contributors. More ions mean greater conductivity, like a highway with more cars. But the size of those ions and how they interact with the solvent molecules also matters. Smaller ions that don't clump up too much can move around more easily, leading to better conductivity.
So it's like a crowded dance floor for the ions. Smaller ones can navigate better. What about the solvent itself? Does that make a difference?
Of course. The solvent's properties, like its viscosity, can either hinder or facilitate that ion movement.
Viscosity, like how thick or sticky it is.
Exactly. A more viscous solvent makes it harder for the ions to move freely. And we can't forget about temperature. Generally, higher temperatures mean better conductivity because those ions have more energy to move around.
So there's a whole dance happening in the solution, but how do we actually measure this conductivity? Is it like sticking a voltmeter in there?
We use a device called a conductivity cell. It has 2 platinum electrodes, usually coated with platinum black, placed a specific distance apart. We measure the resistance between those electrodes, and from that, we can calculate the conductivity, which is often represented by the Greek letter kappa.
Okay, so lower resistance means better conductivity. You also mentioned that conductivity depends on the concentration of the electrolyte, right?
Yeah.
Is there a way to account for that and get like a more standardized measurement?
That's a great point. That brings us to molar conductivity, represented by the Greek letter lambda mdm. It's essentially the conductivity normalized by the concentration, giving us the conductivity per mole of the electrolyte.
Yeah.
This makes it easier to compare different solutions.
So we're factoring out the concentration to see how well the electrolyte itself conducts.
Pretty clever.
But how does this molar conductivity change with concentration? Is there any kind of pattern?
The behavior actually depends on whether we're talking about a strong electrolyte or a weak electrolyte. Strong electrolytes, which fully dissociate into ions in solution, show a slow increase in molar conductivity as we dilute them.
Dilute, meaning adding more solvent and decreasing the concentration.
Exactly. And this increase can be described by an equation that relates molar conductivity to the square root of the concentration. If you were to plot molar conductivity against the square root of concentration, you'd get a straight line.
So a nice linear relationship for strong electrolytes. What about those shy, weak electrolytes that don't fully dissociate? Do they follow the same trend?
Not quite. Weak electrolytes show a much steeper increase in molar conductivity with dilution, particularly at lower concentrations. This is because as we dilute the solution, more of that weak electrolyte dissociates into ions, leading to a big jump in conductivity.
It's like they're finally breaking free. But if the increase is so steep at those low concentrations, how do we figure out the molar conductivity at infinite dilution, where it's completely dissociated?
Right.
Doesn't seem like we could just extrapolate.
You're right. Extrapolation wouldn't work in this case. But thankfully, we have Kohlrausch's law to help us out.
Ooh, a law. Tell me more.
Kohlrausch, being a clever scientist, noticed a fascinating pattern in the limiting molar conductivities of strong electrolytes. He found that the difference in the limiting molar conductivities of two electrolytes with a common ion was always the same. For example, the difference between potassium chloride and sodium chloride is constant, no matter the concentration.
So predictable difference based on the concession. What did he conclude from that?
Well, he brilliantly deduced that the limiting molar conductivity of an electrolyte is just the sum of the individual contributions of its cation and anion. This became known as Kohlrausch's law of independent migration of ions.
So each ion has its own conductivity value. How do we actually apply this law?
Well, for one, we can use it to calculate the limiting molar conductivity of any electrolyte if we know the individual ionic conductivities. There are tables that list these values, so it's like having a recipe book for conductivity.
So we can mix and match ionic conductivities. Are there other uses for this law?
Remember our problem with those weak electrolytes? We couldn't extrapolate to find their limiting molar conductivity. Well, Kohlrausch's law provides a workaround. We can use it to determine the limiting molar conductivity of a weak electrolyte, even though it never fully dissociates at any measurable concentration.
Like a clever trick to solve a tricky problem.
Yeah.
We've been talking about the flow of ions, but what about the reactions happening at those electrodes? How do they fit into this picture of conductance and conductivity?
That's a great question. While the ions carry the current through the solution, the actual oxidation and reduction reactions are happening at the surfaces of those electrodes.
So the solutions, like the highway and the electrodes, are the destinations where the action takes place.
Exactly. And this brings us back to those electrolytic cells we talked about earlier. Remember, they use external electrical energy to drive non-spontaneous reactions.
It's like we're forcing the electrons to go against their natural inclination. But how do we control this process? What determines the products formed during electrolysis?
That's where things get a bit more intricate. It depends on several factors, including the nature of the electrolyte, the type of electrodes used, and the standard electrode potentials of the species involved.
So it's like a competition between possible reactions, and the one with the most favorable electrode potential wins.
You're on the right track. But it's not always so simple. Sometimes, even though a reaction is thermodynamically possible, it might be very slow. In these cases, we need to apply extra voltage called an overpotential to make it happen.
So we need to overcome an energy barrier. Can you give me an example of how the products of electrolysis can be different depending on these factors?
Absolutely. Let's take the electrolysis of sodium chloride, NaCl. If we use molten NaCl, where we only have Na plus and Cl ions, the products are straightforward. We get sodium metal at the cathode and chlorine gas at the anode.
So the ions are getting directly reduced and oxidized, forming pure elements.
Exactly. But if we use an aqueous solution of NaCl, things change. Now we have H plus and OH ions from water in the mix, and that changes the game completely.
So now there's competition. Who wins in this electrochemical battle royale?
Well, at the cathode, we have a showdown between the reduction of sodium ions to sodium metal and the reduction of hydrogen ions to hydrogen gas. Hydrogen ions have a higher standard electrode potential, so they win, and hydrogen gas is produced.
So even though sodium is there, hydrogen gets produced instead.
Exactly. And at the anode, there's a similar competition. Thermodynamically, the oxidation of water to oxygen gas is favored. But due to something called the overpotential of oxygen, the oxidation of chloride ions to chlorine gas actually wins out.
So overpotential throws a wrench in the works. It's like the underdog wins the race. But if water is getting involved at the cathode, producing hydrogen gas and hydroxide ions, that must change the solution, right?
Absolutely. The net result of electrolyzing an aqueous NaCl solution is actually the production of sodium hydroxide, chlorine gas, and hydrogen gas.
So we're making new compounds, not just elements, it's like alchemy, but with electricity.
Yeah.
This is incredible. We've gone from the basic principles of electrochemical cells to the complexities of electrolysis. It's like a whole new world is opening up. But I'm also curious about those practical little devices we use every day, batteries. Can we talk about them now?
Absolutely. Batteries are a perfect example of how electrochemistry powers our lives, and there's a whole range of different battery types, each with its own unique chemistry.
Okay, I'm ready to get energized.
Yeah.
Let's dive into the world of batteries.
Let's start with the ones we use most often, those primary batteries. They're non-rechargeable, single-use batteries that power so many of our, everyday devices.
So once they're drained, they're done. No second chances.
That's right. The chemical reactions inside have, run their course. A classic example is the dry cell, also known as the Leclanche cell. You'll find these in, just about every household gadget.
Ah, the good old dry cell. I'm picturing that classic cylindrical shape with the plus and minus signs on the ends.
Exactly. Inside that familiar cylinder is a zinc container, which acts as the anode. And at the center is a carbon rod surrounded by a mix of manganese dioxide and carbon, forming the cathode.
So zinc on the outside, carbon on the inside. What connects them?
The space between is filled with a paste of ammonium chloride and zinc chloride, which serves as the electrolyte.
Okay, so we've got our players in place. What's the electrochemical action happening inside that dry cell?
The zinc at the anode gets oxidized, releasing electrons. Those electrons flow through the external circuit, powering your device, and arrive at the cathode, where the manganese dioxide gets reduced by accepting those electrons.
So it's a flow of electrons from anode to cathode, powering our devices along the way.
What about those other compounds in the paste, the ammonium chloride and zinc chloride? What are they doing?
They're crucial for maintaining that balance of charge. For example, the ammonia produced at the cathode, it forms a complex with the zinc ions, which helps prevent a buildup of positive charge near the anode.
So it's a carefully balanced system, and all of this produces a potential of about 1.5 volts, right?
That's right, making it perfect for many, common applications. But some devices, like watches or hearing aids, they need a lower current.
So electrochemistry has a solution for that, too.
Of course. For those, we have the mercury cell. It's known for its compact size and stable voltage output, making it ideal for, small gadgets.
Okay, so it's called a mercury cell. Is it as small as the dry cell?
Even smaller. It uses a zinc-mercury amalgam as the anode and a paste of mercury oxide and carbon as the cathode.
Amalgam, that sounds intriguing. It's basically a mixture of mercury with another metal, in this case, zinc. The electrolyte is a paste of potassium hydroxide and zinc oxide.
So another carefully designed combination. What's the electrochemical story unfolding in this tiny battery?
The zinc in the amalgam gets oxidized at the anode, releasing electrons. Those electrons flow through the circuit, and at the cathode, mercury oxide is reduced by accepting the electrons.
So again, we have electron flow from anode to cathode. But you mentioned the mercury cell has a really constant voltage output. What makes that happen?
Well, the overall reaction in the mercury cell, it doesn't involve any ions in solution whose concentration changes significantly over its lifetime. This leads to a very stable voltage, which is super important for, sensitive electronics.
Let's say battery with built-in voltage control.
Yeah.
Impressive. But I'm guessing these mercury cells also have a limited lifespan, like the dry cells.
That's right. They're primary batteries, so once the reactions are done, they're done.
Okay, so those are our single-use options. But what about situations where we need rechargeable power? Does electrochemistry have an answer for that too?
Absolutely. That's where secondary batteries come in. These are the powerhouses that can be recharged and reused many times. They power everything from smartphones and laptops to, electric vehicles.
Rechargeable batteries. Now we're talking. I'm curious, how do they How do they pull off this recharging magic? Is it like reversing the chemical reactions?
You're exactly right. Secondary batteries allow us to reverse those reactions by applying an external electrical current. This charging process essentially restores the chemical species that were used up during discharge.
So it's like giving the battery a fresh supply of reactants. Can we see this in action? I'd love to kind of understand how this recharging process actually works.
Let's take a look at the lead storage battery, the one you'll find in most cars. It's a classic example of a secondary battery with a long history of reliable performance.
The lead storage battery. I'm picturing that bulky rectangular battery under the hood of a car.
You got it. It might not be the most compact, but it's powerful and durable. It's made up of a lead anode and a lead dioxide cathode, both submerged in a sulfuric acid solution, which acts as the electrolyte.
So lead dioxide are the key players here. What happens when the battery is being used during discharge?
At the anode, the lead reacts with sulfate ions from the sulfuric acid, forming lead sulfate and releasing electrons. Those electrons then flow through the external circuit, powering the car's electrical system.
So the anode is the source of electrons, as usual. What's going on at the cathode?
At the cathode, the lead dioxide reacts with sulfate ions and hydrogen ions from the sulfuric acid, accepting the electrons and forming lead sulfate and water.
So both electrodes end up forming lead sulfate. Interesting. What about the sulfuric acid? Does it get used up during discharge?
Yes, its concentration decreases as sulfate ions are consumed. That's actually how you can check the charge of a lead storage battery by measuring the density of the sulfuric acid. A lower density means the battery is discharged.
So the electrolyte itself gives us a clue about the battery's charge. Clever. But what happens during charging? How do we reverse this whole process?
During charging, we apply an external voltage, which forces those reactions to go in the opposite direction. At the anode, the lead sulfate is converted back to lead, and at the cathode, it's converted back to lead dioxide. Sulfate ions are released back into the solution, replenishing the sulfuric acid.
So we're basically cleaning off those lead sulfate deposits and restoring the electrodes to their original state, like giving the battery a brand new start.
Exactly. And we can repeat this charging and discharging cycle many times, making the lead storage battery a reliable and reusable power source.
It's amazing how we can reverse these reactions. Are there any downsides to these lead storage batteries?
Well, they are bulky and heavy, which isn't ideal for every application, and they contain lead, which is toxic, so they need to be handled and recycled, very carefully.
So environmental considerations are important. Are there other types of rechargeable batteries that address those concerns?
Yes. One example is the nickel-cadmium cell, often called a night-Si battery. It's known for having a longer life than lead-acid batteries and handling higher discharge rates.
So a more robust option.
Yeah.
What's the chemistry behind these night-side batteries?
They use a cadmium anode and a nickel oxyhydroxide cathode with a potassium hydroxide solution as the electrolyte. The reactions during discharge and charge are kind of similar to the lead-acid battery, involving the formation and conversion of metal hydroxides.
Okay, so different chemistry, but the same basic concept of reversible reactions.
Yeah.
You mentioned they're more expensive, though. Why is that?
Well, the materials, especially cadmium, are more costly, and the manufacturing process is more complex. But the longer lifespan and improved performance can make up for that higher price in certain applications.
It's always a balancing act between cost and performance. It's amazing how electrochemistry offers such a diverse range of battery options. But all the batteries we've discussed so far, they rely on, stored chemical energy. What about harnessing energy directly from fuels? Is that even possible?
That's a fantastic question, and it leads us to a really exciting area of electrochemistry: fuel cells.
Fuel cells. I've heard that term, but I'm not sure I fully understand them. Are they like batteries, but they use fuel to generate electricity?
You got it. Fuel cells are electrochemical devices that directly convert the chemical energy of a fuel into electrical energy. Think of them as continuous batteries, constantly being replenished with fuel to keep that electricity flowing.
So no need for recharging. That sounds incredible. How do they work? And what kind of fuels can they use?
One of the most well-known is the hydrogen-oxygen fuel cell, which was famously used in the Apollo missions to power the spacecraft.
Space-age technology. Tell me more.
This type of fuel cell uses hydrogen as the fuel and oxygen as the oxidant. They react electrochemically to produce water, releasing energy in the process.
So we're talking clean energy here.
Yeah.
Just water as a byproduct.
Exactly. Fuel cells are so appealing because they're highly efficient and environmentally friendly.
Okay. But I'm still a bit fuzzy on how they actually work. What's the setup like?
In a hydrogen-oxygen fuel cell, both the hydrogen and oxygen are bubbled through porous carbon electrodes that are immersed in a concentrated potassium hydroxide solution, which serves as the electrolyte.
So there are separate compartments for the hydrogen and oxygen.
That's right. And there's another key element. The electrodes are coated with catalysts, usually platinum or palladium, to speed up the reactions.
Catalyst.
Uh,
Always there to make those reactions happen faster. What are the actual reactions happening at the electrodes?
At the anode, the hydrogen is oxidized, releasing electrons. Those electrons flow through the external circuit, and at the cathode, the oxygen is reduced by accepting the electrons and reacting with water to form hydroxide ions.
So once again, we have electron flow powering the device, but this time the overall reaction is just hydrogen combining with oxygen to make water.
Precisely. And the beauty is, as long as we keep supplying hydrogen and oxygen, the fuel cell will just keep generating electricity.
It's like a tiny clean power plant.
You mentioned that fuel cells are much more efficient than traditional power plants. How much more efficient are we talking?
Well, fuel cells can convert chemical energy into electrical energy with efficiencies of around 70%. That's significantly higher than the, 40% efficiency typical of thermal power plants.
It's a huge difference. Less wasted energy means more power. Are fuel cells being used in any real-world applications yet?
They've been used in some niche applications, like in spacecraft and a few demonstration projects, but their widespread use faces some challenges.
What kind of challenges?
The cost of fuel cells, particularly those precious metal catalysts, is a major hurdle. Storing and transporting hydrogen, which is flammable, is also, tricky. And the infrastructure for producing and distributing hydrogen on a large scale is still being developed. So there are some logistical and economic hurdles to overcome, but with all their advantages, I can see why people are working so hard to make fuel cells like a reality. It seems like we've been focusing on how we can use electrochemistry to benefit us. Or are there any downsides to this powerful force? Can it also cause problems?
That's an excellent point. It brings us to a phenomenon we see all too often: corrosion.
Corrosion, like rust. What does that have to do with electrochemistry?
Corrosion is an electrochemical process at its core. It involves the oxidation of metals, which leads to the formation of oxides or other compounds that deteriorate the metal.
So it's like an unwanted electrochemical reaction.
Exactly. Rusting of iron is a classic example. It happens when iron is exposed to both water and oxygen.
Water and oxygen essential for life, but they cause rust. It's kind of ironic. But how does this rusting process actually work? What's the electrochemical angle?
Imagine a piece of iron out in the elements. On a microscopic level, different areas on that iron surface develop, slightly different electrochemical potentials, creating tiny anodes and cathodes.
So the iron itself is like a miniature battery.
That's a great way to think about it. At those anodic regions, iron gets oxidized, losing electrons and forming iron ions. Those electrons flow through the iron to the cathodic regions, where oxygen from the air is reduced, accepting the electrons and reacting with water to form hydroxide ions.
So we have electron flow, just like in a battery, but this time it's causing the iron to break down.
Yeah.
What happens to those iron ions formed at the anode?
They react further with oxygen and water, eventually forming hydrated iron oxide, which is that reddish-brown substance we know as rust.
So it's a chain reaction of oxidation and reduction that turns the iron into rust. That's fascinating, but also a bit depressing. Can we do anything to stop this rust monster?
Luckily, there are ways to fight back. One common method is to coat the metal surface with a protective barrier, like paint or a sealant. This prevents contact with water and oxygen, effectively stopping the rusting process in its tracks.
So we're like shielding the iron from the elements. What other methods are there?
Another approach is using something called sacrificial electrodes. This involves attaching a more reactive metal, like zinc or magnesium, to the iron. Because these metals oxidize more easily than iron, they corrode first, sacrificing themselves to protect the iron.
That's like a noble act of electrochemical self-sacrifice. It's pretty neat. Thinking back to those fuel cells, we talk about some of the difficulties with storing and transporting hydrogen. Is there any connection between those challenges and corrosion?
That's a really sharp observation. Storing and transporting hydrogen are indeed major hurdles for developing a hydrogen-based energy system, and corrosion is a big part of that problem.
Really? How so?
Well, hydrogen is a very reactive element, and it can actually make many materials, including metals, brittle. This can make them prone to cracking and failure, which is a serious concern for, storage tanks and pipelines designed to handle hydrogen.
So even though hydrogen is a clean fuel when it's burned, its storage and handling pose their own, like, problems.
Exactly. Researchers are actively developing new materials and coatings that can resist that hydrogen embrittlement and corrosion to help create a safer and more reliable hydrogen infrastructure.
It's a reminder that as we embrace new technologies, we need to be mindful of the potential downsides and find solutions to mitigate them. It's a constant balance between, like, progress and responsibility.
I completely agree. And this leads to an important point about the future of energy and electrochemistry. We've discussed the limitations of fossil fuels and the promise of fuel cells. Underpinning all of this is the concept of the hydrogen economy.
Hydrogen economy.
Yeah.
I'm intrigued. What does that involve?
It's a vision for a future where hydrogen, a clean and renewable energy carrier, plays a central role in powering our world. Imagine a world where we produce hydrogen from renewable sources like solar or wind power, and then use it to generate electricity in fuel cells to power our homes, businesses, and transportation systems.
It sounds like a utopia of clean energy. But we've talked about those challenges with storing and transporting hydrogen. How realistic is this vision?
The hydrogen economy faces, significant challenges, but it also holds immense potential, and electrochemistry is at the heart of it all.
Really? How so?
Remember electrolysis, that process we talked about earlier where we use electricity to split water into hydrogen and oxygen? That's crucial for producing hydrogen from renewable sources. And fuel cells, as we discussed, are the key to converting that hydrogen's chemical energy into electricity.
So electrochemistry is both the creator and the enabler of this potential hydrogen-powered future. That's incredible.
Exactly. It really highlights how important electrochemistry will be in shaping a more sustainable energy landscape.
This has been mind-blowing. We've explored the world of electrochemistry from its basic principles to its applications in batteries, fuel cells, and even corrosion. It's a field that touches so many aspects of our lives, from the everyday devices we rely on to the global challenges we face. It feels like we've covered so much ground. I'm almost feeling like a bit overwhelmed. Is there a way to sum up all of this, to capture the essence of what we've learned?
Well, electrochemistry at its core is the study of how chemical reactions and electrical energy interact. It encompasses a vast array of phenomena, from generating electricity in batteries and fuel cells to the processes of electrolysis and corrosion. It's both fundamental to our understanding of the natural world and crucial for developing new technologies to address some of the biggest challenges humanity faces.
That's a great summary, but what does all of this mean for our listener? Why should they care about electrochemistry?
Electrochemistry is all around us. It's what powers our devices, drives industrial processes, and plays a key role in both our bodies and the environment. Understanding the principles of electrochemistry allows us to make informed decisions about the technologies we use, the energy sources we rely on, and the impact we have on our planet.
That's a really powerful message. Electrochemistry is not just an abstract concept. It's a force that shapes our lives in, like, profound ways. It really feels like electrochemistry is like a key to unlocking a more sustainable and energized future. But where can our listener go from here? What can they do to explore this fascinating field further?
Well, there's so many avenues to, delve deeper. The internet is a treasure trove of information, websites, videos, articles, you name it. There's a wealth of resources out there just waiting to be explored. And don't be afraid to get hands-on. There are simple electrochemistry experiments you can try at home or even in a school lab to see these principles in action.
I love that idea of getting hands-on and experimenting. For those who want to take a really deep dive, there's always the option of, like, taking courses or reading books to expand their knowledge.
Absolutely. And the most important thing is to stay curious and keep asking questions. Electrochemistry is a dynamic field, constantly evolving with new discoveries and innovations emerging, all the time.
This deep dive has been an incredible journey. We've explored the foundations of electrochemical cells, delved into the intricacies of electrolysis, and uncovered the power of batteries and the promise of fuel cells. We even touched on the challenges of corrosion. It's a field that impacts our lives in countless ways.
I hope this deep dive has sparked your curiosity and inspired you to learn more about this exciting world of electrochemistry. Keep exploring, keep asking questions, and keep an eye out for the electrochemical wonders that are, all around you.
And remember, electrochemistry is more than just like equations and reactions. It's about understanding the flow of energy that powers our lives and shapes our future. So stay charged up and keep exploring the wonders of the electrochemical universe.